Okay, stats lesson 6.38. I forgot the header. We're doing binomial distributions. This is we're breaking this into pieces. So let's get started. These slides aren't ideal. There's a lot of words here. My apologies. So just for now, fill in the blanks. Okay, we're interested in whether a particular outcome happens each time. The number of trials fixed in advance, and we're interested in the number of trials success occurs in these trials. Okay, if they're independent and each one has an equal chance of winning, and it's a binomial. So we're going to use bins here. Okay. So B in bins is it binary? It means the possible outcomes are classified as either success or failure. Right? Think of like computer as a binary system. You have ones and zeros. The I stands for independent. One trial does not have anything to do with another trial. Like it's not going to give us any information about the next trial that comes, like flipping a coin. Okay. And N, the number. The number of trials must be determined in advance. Okay. And then S stands for success. The probability of success in this case. And that's P. Okay. And here we had the letter N. So P is the same for each trial. We're using large X. It's going to be our count of successes for a binomial random variable. And then the probability distribution is a binomial distribution with N and P. So we're counting our successes. And then we have a binomial distribution. So N is the number of trials. And P is the probability of success. And these are going to, in our X's, our number of trials are going to be whole numbers from 0 to N. Go ahead and read this. We're talking about shuffling cards. Let's determine if it is a binomial, if it has a binomial distribution. Bins. B is a binomial. How do we define success and failure? So success equals an ace. A failure is not an ace. So that's binomial. Two outcomes, success and failure. Independent because we're replacing the card and shuffling the deck. We have a predetermined number of trials. It's 10, so that's good. And then our probability of success is there's 4 aces in a 52 card deck, and each time we replace, our probability remains the same. So let's check against bins. Now we're going to shuffle, turn over the top card, same thing, repeat 10 times, but something's missing. So B, we have success or failure. Ace, not ace. I, independent, no. Because we're not replacing the card, let's go down to our success. Probability of success. It varies. Varies. That doesn't understand. With each draw. So my first card has a probability of 4 out of 52. If it's an ace, then the next card has a 3 out of 51 chance of being an ace. If that first card's not an ace, then the next card has a chance of 4 out of 51. And so on and so forth. And this probability tree will branch out and get ridiculous. So it is not binomial. Okay. Remember, P has to be the same for each trial. So now we start getting into some math, okay? For any setting in which we're interested in K number of successes. So we have N number of trials is total thing we're going to do. And then we're trying to see how many successes. What are the chances we have? We draw 3 aces out of our 10 trials from the previous example, okay? So that's going to be the number. We're looking for the total number of arrangements that we can have success. What if the first two times we get an ace and then the last one we get an ace? That's a different arrangement than if we get 3 aces in a row from our last example. The same as if our last 3 trials are successful. Okay, so how many different ways can we have success 3 times out of 10 trials using our last example? So the definition is our number of ways of arranging K successes among N observations is given by a binomial coefficient. And it's N choose K is how we say that. Okay, and that's going to be N factorial divided by K factorial times N minus K factorial. And so here's another notation. It's NCK, and that's a combination because order doesn't matter. All right, so this is for K equals anything up to N, where N factorial equals all your guys here, and 0 factorial equals 1. So you can find it on your calculator under math, PRB, and then N CR. So binomial probability, okay, is going to be if X has binomial distribution. So we checked it first using bins, right? So we used bins. We know it's binomial, okay, that it has a binomial distribution. Okay, so here's how we want K number of successes. So we have N trials, K successes are we looking for. This is our coefficient. And we are multiplying it times this value here, okay? The probability of success raised to the kth power times the probability of the complement, so failure raised to the n minus k power. This is the same notation here, or different notation, but it's the same value. Here we have an example. We have a family, 2 parents. They have exactly 5 children. I'm trying to highlight here. Any one child has a probability of 0.25 of having type O blood. Okay, so find the probability exactly 3 children have type O blood. I'm going to write this out and then we'll go through it. Okay, so I wrote it out. What's the probability? Remember, X is our very random variable, and that is 3 of the children have type O blood. X is number of children have type O blood equals 3. There's 5 children. Well, the chance that 3 of them, any 3, have type O blood. This is a binomial distribution because if the first child is type O, that has nothing to do necessarily with the next child, whether or not they're going to be type O. This is oversimplification, but we're just going to use it. So we have 5 choose 3. We have 0.25 for type O. This is our success probability, and it's raised to the 3rd power because it's raised to k. K is our 3 here. It's a number of successes. Then we multiply it times the complement, which is 1 minus 0.25, so that's 0.75. We raise that to n minus k, so that's the difference between our number of trials and our number of successes. So we have 3 successes, and we should have 2 failures, meaning 2 of the children do not have type O blood. So 5 choose 3, that's 10, so the binomial coefficient is 10. This is the same, so when we do the maths here, we get 0.0879. In context, there's an 8.79% chance that 3 of the children have type O blood. Let's work the next example. So what's the probability that more than 3 have type O blood? So X is our number of children that have type O blood. Probability that X is greater than 3. Well, only 2 options out of N trials, being 5, is probability that 4 of them do, or the probability that 5 of them do. Sorry, it's or. So 4 or 5 would satisfy this condition. So I have 5 choose 4 times 0.25 to the 4th power times 0.75 to the 1st power. This is the probability that exactly 4 of them have type O blood, and I add to that the probability that exactly 5 of them, all of them. 5 choose 5. That can only be done one way. 0.25 to the 5th power times 0.75 to the 0. Remember, this is n minus k. This is k. N minus k, k. When you add these exponents, it should add up to your total number of trials. Do the maths. Your binomial coefficient for 5 choose 4 is 5. You multiply it through. And then for here, binomial 5 choose 5 can only happen one way. 0.75 to the 0 power is 1. Do the maths again, you get 0.0156. In context, so answering in context, there is a 1.56% chance that more than 3 children have type O blood. So how do we use our calculator to streamline this process? So for our example, where we have exactly 3 from the children, remember? So what's the probability X equals this very specific number? You're going to use binomial PDF for the exact point distribution. So it's binomial PDF, and then you're going to have these inputs. Number of trials, it's right there. Probability of success, that's your value for P. And the number value from the probability, that's your X value. No, number value from the probability. Oh, how many successes you want. So N, P equals, that's your decimal value, and this is, X is actually your K in this situation, okay? Then you're going to have what's probability that X is less than or equal to some number. So that's accumulation. So think about like you have your probability distribution, and you're filling the space underneath a curve. So you're going to use binomial CDF, your number of trials, that's your N, probability of success, that's your P, it's a decimal, and the number value from the probability. This is actually your K. It's the number of successes you're looking for, X value. All right? Probability X is greater than or equal to some number. Well, the CDF gives us up to a number, so this we're going to have to take 1 minus the probability that X is less than or equal to this number minus 1. So think about it this way. If it's probability that X is greater than or equal to 5, okay, well, I can't use CDF because CDF gives me all this shaded area up to 5. So I need this over here. So in order to find that, we're actually going to look for what's the we're going to take 1 minus the probability that X is less than or equal to 4. Okay. Because remember, our number of trials, they're discrete values, they're countable values. So that's what we're going to do. So here, we're using binomial CDF. Okay. Number of trials, that's N. Our P goes here, same for success, but our X value here is going to be this value, this number, minus 1. So instead of 5, now it's 4 goes there. All right, so what's the probability X is greater than a number? Well, it's very similar. It's 1 minus the probability that X is less than or equal to that number. So let's say, what's the probability that X is greater than 5? Well, we want 1 minus the probability that X is less than or equal to 5 because this cannot equal 5. So I'm starting above 5. So essentially 6, 7, 8, and so on. So I want 1 minus the probability that X is less than or equal to 5. And so I have 1 minus binomial CDF, number of trials, N, probability of success, your decimal, and then your K value. It's this K value goes here. Lastly, probability X is less than a number, using the same thing here, except, so we have number of trials, probability of success, that's your P value, and then the value from the probability minus 1. So it's this number, subtract from 1, okay? And that's it. That's what we put in our calculator. We're going to speed through this example. Pause and read this. Now, show that X is a binomial random variable. We're going to use bins to see if it's a random variable. Is it binomial? Meaning, is there success and failure, nothing else? Success is the right answer, failure is the wrong answer, so R and W. It's independent because the answers are randomly assigned. We have a predetermined number of trials, which is 10, and our probability of success is uniform. It's the same for each trial. It's 1/5, it's 0.2. So, what's the chance that Patty guesses exactly 3 right out of 10? So it's probability that X equals 3. That's 10, choose 3. Here's our probability for success. It's 0.2 for each question. K number of successes, 3. Failure is 0.8, and there's 7 failures, right? That's N minus K. You do the math, or you plug it into binorm PDF on your calculator, and you get 0.2013. That means there's about a 20% chance that Patty guesses exactly 3 correct. I just recorded. I just said all that without recording. Great. So, did you get a passing score by guessing 6 times or more? So we're looking for the probability that there's at least 6, so 6 or more correct answers. But we find that by taking the complement. 1 minus the probability that the number of correct guesses is less than or equal to 5. It's 1 minus binomial CDF. Number of trials is 10. Probability of success is 0.2. Number of successes, which is K, is 5. That equals 0.0064, which means there's about a 0.64% chance of passing by guessing. I would be very surprised if Patty passed by guessing.